Hi there. Today we're going to be looking at acid-base neutralization. And we're going to look at two different examples of acid-base neutralization, one with strong acids and strong bases, and then one with weak acids and weak bases, because each situation is a little bit different. So let's start with one of the easier ones, which is strong acids reacting with strong bases. When a strong acid and a strong base react with one another, they always form a salt, and a salt is just another word for an ionic compound. And if you recall from the past when we talked about ionic compounds are formed out of a metal and a nonmetal, or a metal and a polyatomic ion. In other words, a cation, a positive ion, and an anion, a negative ion. The other thing that strong acid and strong base always form is H bonded to OH, hydrogen hydroxide, which of course is just water. But it's a little easier to look at it as HOH because we're taking hydrogen from the strong acid and bonding it to hydroxide from the strong base. So let's look at an example of this type of reaction and see what's going on. Let's try an acid that you guys are very familiar with, which is hydrochloric acid. We've used that many times in class. And in order for an acid to be an acid, it has to be dissolved in water. So notice I'm putting AQ. And let's react it with sodium hydroxide, which is a strong base. And again, a strong base has to be dissolved in water to act like a base. And when an acid and base react, they react completely. It's a complete reaction. It doesn't set up an equilibrium. So we draw a arrow going only one way. And when this happens, we're going to have a double replacement reaction. Strong acids and strong bases always undergo a double replacement reaction. The hydrogen is going to replace the sodium, and the sodium is going to replace the hydrogen. So what will the sodium be bonded to when it replaces the hydrogen? Well, of course, the sodium will be bonded to the chloride. So we write our formula, Na, sodium, bonded to Cl, chloride. And remember, chloride is 1 negative, and sodium is 1 positive, and so we have to cross the charges to get the formula for the sodium chloride, which is cross the 1, chloride with a subscriptive 1, and cross the 1, sodium with a subscriptive 1. So we get sodium chloride, and since we have water present, and sodium chloride is soluble, we write AQ. Then the hydrogen is going to replace the sodium and be bonded to hydroxide now. So hydrogen bonded to hydroxide. And remember, we said that is simply water, but this is just another way of writing water. And water under normal conditions is a liquid. So we end up with our strong acid reacting with our strong base, and notice we make the ionic compound sodium chloride, which is a salt, and we make liquid water. So this followed exactly what we said it would. Strong acids and strong base make a salt and water. Let's try another reaction, another strong acid, strong base reaction. Let's take some sulfuric acid, H2SO4, and let's react it with another strong base, KOH, potassium hydroxide. So again, we're going to have a double replacement reaction. This ionic compound is going to react with this ionic compound. So the hydrogen will replace the potassium, and the potassium will replace the hydrogen. So when this happens, K will then be bonded to SO4, sulfate. So potassium is going to bond to sulfate, SO4. And remember, potassium is 1 positive, and sulfate, if you look on your polyatomic ion sheet, is 2 negative. So we're going to have to cross the 2 and the 1 over here. Cross sulfate's 2 charge and make it K2, and cross potassium's 1 down to SO4 and just have SO4 1, but we don't write 1s. So K2SO4 is our formula for this compound. Very important to cross those charges. And then hydrogen is going to be bonded to hydroxide. Hydrogen is 1 positive, and hydroxide is 1 negative, so it just makes HOH, which again is a liquid. So now we need to balance it, because notice we have, it's unbalanced. So here we have 2 potassiums, so on the left-hand side, we need to put a 2. Over on this side, we have 2 hydrogens, and we have 2 hydroxides. So we need to put a coefficient of 2 to make 2 hydrogens and 2 hydroxides. And so now this reaction is balanced. Again, we made a salt, an ionic compound, and water, H2O. So strong acid and strong base, not too bad. Very familiar with these double replacement reactions, so nothing too new here. But weak acids and weak bases, sometimes you have to look at them a little bit differently. So let's look at an example of weak acids and weak bases. So we've talked about a few weak acids, and one weak acid we've looked at is hydrogen fluoride, or hydrofluoric acid. Hydrofluoric acid is HF. Notice it's very similar to hydrochloric acid, but it has fluorine. And then let's react it with a weak base that we've talked about a whole lot, which is ammonia, NH3. Now in this particular reaction, there will be an equilibrium. The weak acid and weak base will go both ways, because weak acids and weak bases do not ionize completely. The hydrogen does not transfer completely. And that's another thing that's a little different about this, is that we're not going to have a double replacement reaction, because we don't have two substances that ionize. We have one substance with the hydrogen that's going to donate the proton, and one substance that will accept the proton. So what's going to happen here is this hydrogen is going to transfer over to the base, and it's going to lose a hydrogen. The base will gain a hydrogen. So when this happens, when the fluoride loses that hydrogen, it loses its positive ion that it was bonded to, so now just the fluoride is going to be left. Remember, fluoride is negative, so it's going to be F negative after it loses that hydrogen. The base, ammonia, is going to gain the proton, the hydrogen ion. And when it gains that hydrogen ion, now it's going to have 4 hydrogens. And because the hydrogen it gained was positively charged, the overall NH4 has a positive charge. And this will be aqueous also, because it's going to be dissolved in water. So in this acid-base reaction, this weak acid and weak base reaction, the hydrogen just transfers from the acid to the base to form an anion and a new an anion and a new cation. So hydrogen transfer was the key. Let's look at another example. Let's look at another weak acid that we've talked about quite a few times. Acetic acid, CH3COOH. And so this is aqueous. And let's react it with something a little tricky. Let's react it with a negative ion, BrO3. Now, you can't just have a negative ion floating around in water. There has to be a positive ion to balance it out. And in this particular case, sodium was the positive ion bonded to it, but the sodium's not going to react in this reaction. So what I've done is left it out. So we're just going to look at what's called the net ionic equation. We're going to look at just the ions that are reacting. So bromate is going to be the ion that's going to react here. So again, this is a weak acid, and it's going to react with substance that can gain a hydrogen, so it's going to be a weak base. This hydrogen is going to transfer from the acid to the base, and it's going to set up an equilibrium again. So what's going to be left when this substance loses the H positive ion? Well, if you said CH3COO minus, you were correct. And it's minus because it lost a positive hydrogen. So CH3COO minus, the acetate ion. And what's going to become of the BrO3 negative when it gains a H positive? Well, the H positive is going to attach itself to the BrO3. So HBrO3. And it's going to be neutral when this happens, because the H was positive and the BrO3 was negative. So that is our final product, the negative acetate ion and the neutral hydrogen bromate, which is bromic acid. So just one last thing to look at. This was our acid originally, and this was our base originally. And how do we know that? This substance lost the hydrogen ion, and this substance gained a hydrogen ion. Remember, the acid, after it loses a hydrogen ion, becomes the conjugate base, and the base becomes the conjugate acid. So just a reminder about that. So that's it. That's our acid-base neutralization. Good luck to you in all of your work.